our final presentation today. It's entitled Implementing Motion Capture Technology for Ergonomic Assessments, and it's presented by Dennis Larson, a postdoctoral researcher from the University of Waterloo. Dennis, over to you.
Okay, thank you for the invitation. As Trevor mentioned, I'm a postdoctoral researcher at the University of Waterloo in Ontario, Canada, and I'm also a practicing associate ergonomist with Pro Ergonomics, Inc. This presentation, if anybody had come to the CRE-MSD presentation on January 27th, is going to be presenting the same information as that. So if you missed anything there, you'll get a review of the topic. But before I begin, I just want to acknowledge all of the collaborators in this project. This is a lot of work to work with all of these external companies to, what I'm going to present is going through these computer vision tools that are going to be used in ergonomics and doing some assessments on the workplace. So without all of their assistance, this data wouldn't have come together. So I want to send a quick thank you to all of them. And to start off, just kind of briefly going to overview a little bit of markerless motion capture and computer vision technology and how they work a little bit. So these technologies incorporate machine learning algorithms to identify key points of the human body from two-dimensional RGB videos or images. So across all of the tools that are out there, there are a variety of different methods to go from a 2D image to a three-dimensional posture or key point. So it's all embedded within their softwares, and they've all been trained with different videos, different data, so there are different models out there. And I'll touch on that in a little bit. But from here, they take a 2D image and go into 3D to create 3D points on the human body to create a 3D skeleton or stick figure that overlays on top of the body in the video itself. So just a couple quick examples of some multi-view or multi-camera methods. On the far left of the screen is Theia Markerless, now rebranded to just Theia. They require at least 6 cameras to see the participant while they're working to reconstruct their pose estimated skeleton on the body. And on the right is an example of OpenPose, which is an open source program that you can use 2 to 3 camera views to determine key points in 3D space. Now, in order for these camera systems to function, you need to perform a calibration procedure so that all the cameras know where they are in space and in relation to global space, and develop a relationship between the 2D pixel coordinates of the image and the 3D position in the world. Now, moving from these multi-view methods to single view methods, these are single cameras that are placed in the workspace or held by an ergonomist or practitioner, taking a video of the person, and they are then taking these 2D images, putting key points on the body, and pulling them into 3D space to get estimates of joint angles using just a single camera. And these don't require any calibration steps or procedures. Now, these single camera computer vision tools have rapidly emerged in the market, and these technologies are used to be like a simple point and record method of videoing workers on the job. And then you take those videos, upload them to their program or application, have it perform the human pose estimation, and then from there you get the 3D postures in space, and you can do all the risk assessments associated with getting those positions in space. Now, this can be used in a very quick period of time to get a very rich amount of data, both body position and joint angle wise. And this is data that we have struggled to capture in the field in a very time and cost efficient manner. And it helps ergonomists and practitioners better evaluate the risks in the field. However, like I said, it's a rapid emergence of these technologies, so there's many, many questions surrounding how to best use these technologies. And some of them that we tried to tackle with this project is there an optimal viewing angle for improved pose estimation accuracy? And an example of this is if you are in a larger company with multiple sites globally or locally, and you have 2 people taking videos of the same task, what if they're from different angles? How does that influence the pose estimation? How do we interpret the data and evaluate it to then do some risk assessments and find some solutions in the field. Another question is, does the speed of motion influence the pose estimation accuracy? Basically, if you're moving faster, there may be possibilities for image blurring, and that could influence the pose estimation accuracy. And then the last one that we wanted to look at is that do outputs from differing computer vision pose estimation tools, do they differ in their accuracy compared to a lab grade system? So we set off to answer all of these questions in a study where we asked among healthy, able-bodied individuals performing a series of simulated occupational tasks, does the angle of video recording, the task pace, or the computer vision approach influence estimated trunk or shoulder elevation angles relative to the angles estimated from a lab grade system or approach? So with this study, we had 40 participants come into the lab. They did 6 different tasks. We had an above shoulder work task where they sorted tags above from pegs about shoulder height to above shoulder height. Cutting and trimming task where we simulated a meat trimming and cutting task that was designed based on a cutting block from Cargill. Simulated packaging task, putting cartons into a box, floor to shoulder lifting, palletizing, and cart pushing and pulling. So we did these 6 tasks. I'm only going to show a subset of 3 data points. So I'm going to show videos of them, those 3 specific tasks in a second. But we also did them at fast and slow speeds. Just to guide that, again, to answer whether there are some issues or potential issues with motion blurring. So just kind of a video of the above shoulder work here. So like I said, participants were sorting tags from the pegs that are at shoulder height up to pegs that are above shoulder height. There's 16 tags altogether, and they were timed to a metronome at both the fast and the slow speeds. For the simulated palletizing task, we had 10 crates being lifted from one side of the force plates that the participant is standing on to the other. Each of them were instrumented or had 10 pounds of weight inside of it. And they, again, moved at fast and slow speeds to the pace of a metronome. And then the last one that we're going to show today is the packaging task. So this is, again, paced to the beat of a metronome, where they picked up containers of Play-Doh, put them in a box, and then at the end of after they put all 10 in, they slid the box over to the left to simulate moving the box along a conveyor belt system. So during all of these tasks that we had in this study, we had 8 cameras that are synchronized all surrounding the participant all the way around the room. So we had some anterior, posterior, immediately sagittal, and then had approximately 45-degree increments in between those 2 extremes. Now, this is what those 8 cameras look like for the simulated palletizing task. And in order to get our reference data or ground truth data that we're going to be using in this study, we pre-process them through Markerless, like I said, which is that system that requires at least 6 cameras to generate a skeletal pose estimated skeleton on the body. So here's just what that kind of looks like from all the different camera angles. And I'm going to quickly show a video here of what it looks like during the palletizing task. Yeah, there we go. So this is just an example of the 3D pose estimated skeleton that is put on top of the participant doing the work. So this is a palletizing task, and this is just from one of the camera views that are on the left side of the participant. Now, each of the 8 camera angles, or each of the 8 cameras, all captured videos all at the same time. Like I said, they were synchronized together, and each of those videos were then uploaded and processed through 4 to 5 separate pose estimation companies. So here's just a quick example or quick picture of what those look like for the palletizing task. But I'm going to show some videos here of what each of the companies, of the 5 different companies that we used, doing that same palletizing task. one's a little bit out of sync there. But one thing I want to point out here is that all of these companies, like I said, they all have different, are all set up differently. So they try to identify key points within the body. They use the key points in slightly different ways in order to generate their skeletal pose estimation and calculate their joint angles. And they're all trained off of different data sets as well. So this creates a little bit of differences across these pose estimation companies. And I'm going to get back to that again in a little bit as well. So for the comparison, we extracted shoulder elevation angles and trunk flexion extension angles from our Thea Markerless data set. So we took our video, uploaded it into Visual 3D, and then from there we calculated the shoulder elevation and trunk angles. And we asked all the companies to calculate these same angles for each of the camera views that we uploaded for them. So we got the shoulder elevation and trunk angles from the pose estimation companies, and we compared them together. So this is just an example graph here where we have angle along the y-axis, data frames or the time that the trial was going on for. Thea data is in black, and then just an example of the different camera views. Here's the different colors, green, red, and blue, representing each of the cameras compared to the Thea. So from there, we determined root mean squared differences between each of the camera view companies and the Thea Markerless data set. So I want to point out that in this field, many researchers would coin this metric or this term as root mean square error, but we are calling it a difference for this study. And the reason for this is that the skeletal or stick figure pose estimation overlays that are estimating our position of our body in space, they're estimating also the position of our underlying skeletal structures, and they may not be exactly replicating the movement. And this is the same for an optical motion capture system as well. You have the reflective markers put on the body, on bony landmarks, but you still have skin motion artifacts. So it's a representation of the movement. It is not directly the skeletal movement that we are measuring. So because of that, anything that deviates from our Thea Markerless data is a difference in this study compared to classifying it as an error. So we're going to hop into some results here. I want to point out before we get any further that we are in the final stages of processing, double checking the data for one of the companies that we are working with. And this project was started over a year ago now. And for all of us, we didn't fully understand the sheer amount of data that we would be working with at the onset of this project. So incredible learning experience. Got over a few roadblocks, almost done with the project, but the data that I'm going to be presenting here is a subset of 3 of the companies instead of all 5. So it's just a representation of the trends that we are seeing so far that are still being seen in the other 2 data sets. We're just finalizing those analyses. So first, we're going to look at shoulder elevation angle on the left side of the body. We're going to specifically do it for the above shoulder work task. Now, before getting into any of the graphs or any of the data, all of the figures that I'm going to be presenting are going to be presented very similarly. So we have root mean squared difference along the y-axis. We have all of the camera angles along the x-axis, starting from anterior, working around the left side, going all the way to the right. And then there's going to be 2 different color bars. The dark blue bars are going to be fast, and the light blue bars are going to be considered slow. So this is going to be the setup for all the figures moving forward. And again, this is going to be the left shoulder elevation angle for the above shoulder work task. So the first thing I'm going to pull up here, this is for the left shoulder, taking the camera view from the left side of the body. This is where we saw the lowest differences between the Thea Markerless data and the 3 companies that we used in this initial analysis to look at the trends. So what I want to quickly point out, so it's around 10 degrees of root mean squared difference. And before I move on any further, I'm going to step back a little bit and maybe address a little bit of elephant in the room regarding this 10-degree difference that I just mentioned. So in this graph here, I'm going to show you the left shoulder elevation angles for the above shoulder work task, and this is just a representative trial for this task from the left camera view that we just talked about. So here's the reference Thea data for the left shoulder elevation angle across the trial. And what I'm going to start doing is populating the graph from all 5 of the companies that we looked at. So I'm just going to start slowly populating these in here. And as we go through and add more in, just looking at the general offsets and biases that some of these data have at certain time points throughout the trial. Some of them being above our reference data set, some of them being below, some of them are going above and below at certain points as well. So going back to what I mentioned previously about how these different companies work, or these different pose estimation algorithms work, we believe that these general offsets and biases are due to how these companies are calculating the joint angles themselves in relationship to how we calculate the Thea Markerless data set. So what do I mean by this? Now, Thea requires a multi-camera setup with the video and image data from at least 6 cameras to generate the 3D pose estimation. So with all of this data, the Thea system can represent body segments like the upper arm, the pelvis, the torso, the thigh. They can use or represent these with 3-dimensional coordinate systems, of which they know the position and orientation in space. And from there, I can calculate the shoulder elevation and trunk flexion extension angles following ISB standards, which many researchers use to calculate angles. Now, with the single camera pose estimation data, they may or may not potentially use some open source computer vision approaches like OpenPose or MediaPipe. So those are open sources that they can use to start building their computer vision algorithm, or they've developed their own algorithm. But they've all kind of share a similarity in that they are looking for key points on the body that are different than what they can use with the multi-camera system. So they have built and trained machine learning models to pull these 2-dimensional key points from these videos into 3D space and create 3D coordinates and calculate the angles between these different vectors that are created between these points along the body. So it's a little bit different in how Thea Markerless does it. So while we best matched our calculations between the Thea data and the computer vision company definitions, the way we are calculating them are still inherently different, which leads to some general biases or offsets between the computer vision company and the data that company data and the data that we collected with Thea. So that's again a reason why we're calling them differences as well. So jumping back to the data that I just mentioned about, or jumping back to the original data that I mentioned with the 10-degree difference between Thea and the 3 computer vision approaches here. We now have what we believe is an explanation for the general root mean squared difference that we are seeing between the companies and the reference data. And now I want to focus in more on the factors such as camera angle and movement speed that may influence the overall accuracy of the single camera computer vision data. So again, this is our best view. Going to the other extreme, we have the worst view. So this would be from the anterior right, where we are seeing larger differences between the Thea Markerless data and our reference and our computer vision companies. Now, the reason for this is that we can see that this is the camera view here from the anterior right-hand side looking at the task. There's partial body occlusions on the contralateral side. So if we're on the right side looking on the left, we're having a hard time seeing the left shoulder, left upper arm to generate those angles. So then we're having these greater differences being generated between the reference data and the Thea Markerless. Now, all the other bars that I just populated in here they are somewhere in between. So we can see that there's a range going, looking at the left side, left shoulder elevation from the left side, and then we see greater differences when we go from the right side, looking at the left shoulder angle. So the key takeaways from here is that a side view of the plane of motion, that is the major joint of movement, so flexion extension in this case, is performing best. So if we are taking the camera view from the left side, left camera view, we're seeing that as working the best. We want to avoid occlusions because that leads to greater differences and not being able to track the motion very well. And then what I didn't point out is that you'll notice that all the letters on the different bars, if they're different, that means they're statistically different from each other for camera angles. And then the asterisks above those letters, that means that there is a statistically significant difference in movement speed. So for some of the, I'm going to call them non-optimal camera views, the ones that are not highlighted in green, the slower pace resulted in larger root mean square differences in those scenarios. Jumping to the right shoulder elevation for the above shoulder work task. So the exact same task, but just looking at the right shoulder instead of the left. Here on this side, right, or the camera angle or camera view from the right side perform best. And looking on the left side or the anterior left perform the worst. So these are just similar results, but just flipped to the right side of the body. So again, I'm going to populate the rest of the bars in there and everything is in between. But again, the key takeaways here, perpendicular view to the plane of motion results in lower differences between the Theia data and the computer vision tools. Avoiding occlusions, again, that is always, if you can't see it, it's not going to track it well. And from here, if we take the left and the right side data together, it shows that we need to record motion on the same joint of interest in order to optimize the results of our computer vision tools. So just quick summary of all of that. Key takeaways so far: video recording angle matters, and there seems to be a limited influence of movement pace, specifically when you look at the videos recorded from the optimal views. Okay. So now we're jumping to a different task here. So the above shoulder work was very stationary, looking straight ahead. Palletizing, we are having rotation of the body, turning back and forth. So we're just going to look at the right shoulder elevation angle for palletizing. Again, the graphs are going to be set up the same. For this task, both the left and the right side produce the lowest root mean square differences, or differences between Theia and the computer vision tools. And then the anterior and the posterior views presented the greatest differences between computer vision companies and our reference data set. So with that being said, again, we're key points here. From the side, we're seeing that we're having the greatest plane of motion, the flexion extension of the shoulder elevation. And when we go to the anterior side, we have those pillars of crates in front and behind that lead to some potential occlusions in the body, and then some greater differences and tracking errors, or tracking differences between the computer vision tools and Theia Markerless. And then the other camera angles kind of fill in the gaps in between. So again, from here, key takeaways, like I said, perpendicular view of the major plane of motion is performing best. And here we're also seeing at those non-optimal views, we're seeing that slower pace is generating some higher RMSD values. Now looking at the trunk angle itself, or the trunk angle during the palletizing task, we haven't looked at that yet. We looked at flexion extension here. Again, looking at the left and the right side, we have the lowest RMSD, but here we're also seeing the anterior right as well. And this may be because some companies have been trained to look at data that way. So that could be resulting in some of the anterior right being involved in the lowest data or lowest differences here. And then again, the anterior and posterior side. we're seeing those largest differences occur there as well. And then the other two camera angles fill in the gap. So again, when looking at the key takeaways again, perpendicular view, major plane of motion, lower root mean square differences or differences. So we're having these better pose estimations of those data when we're looking at sagittally or the side view of the major plane of motion. And there's limited influence of the movement pace on these optimal views. So just to come back, key takeaways here, video recording angle matters, limited influence of movement pace. Again, the movement pace is for those optimal views. So when you get into the suboptimal or non-optimal views, you're starting to see that movement pace being a little bit more of an influence there. So last little bit of data. I know I'm throwing a lot of data at you. This is only a subset of everything that I've been looking at, but here's the right shoulder elevation during packaging. So again, we're looking at the right shoulder, looking at the right side of the body, or having a camera on the right side of the body, we see the lowest differences there. And then on the anterior or anterior left, so looking opposite to where the limb of interest is, we're seeing those larger differences happen there. And again, pointing it out here because it's really clear, those non-optimal views, you're seeing that difference in movement speed, where on the right or that optimal view, you don't see that difference in movement speed. Then the rest of the camera angles or camera views kind of fill in the data in between. So again, sticking back to our key takeaways, side view, major plane of motion, same side of the joint of interest. That's the exact same results that we're seeing with the above shoulder work tasks. So we're seeing it across multiple tasks, as I just pointed there. So we're seeing the similar results across multiple tasks and starting to build a story here. Last little bit with the trunk angle, packaging. Here, it gets a little bit different, but there's a reason for this, I think. So with the trunk angle and packaging, the camera angle with the lowest root mean square difference was the anterior right. And now for this, we were tracking flexion extension. And if you look at the image up in the top right, as the participant is reaching to grasp the containers, they're twisting their body, and their major plane of motion is now in line with that right or anterior right camera view. So again, being sagittal to the major plane of motion. So because we're looking at trunk and flexion, the sagittal view, and as we turn, we're facing that anterior right camera. I think that is why we are seeing this be the lowest or have the lowest difference for this trial or this data. Now, the worst in this scenario is posterior right. So this is looking, if we twisted our body, camera right behind us that way, we're looking at the frontal plane. We don't see the flexion extension axis very well in that plane. So again, we have the greatest differences there. And then all the other camera angles come into play here. So again, key takeaway, camera angle perpendicular to the major plane of motion performing best. Now, with this one, the speed differences are slightly different compared to everything else that I presented. So we're seeing slightly greater root mean square differences in the fast-paced movements across most of the angles for this one. But again, what I'm looking at here is if I compare all the means across these data, while statistically significant, it may be a degree or 2 degrees difference between fast and slow. So the practical implications of this are not large. So again, coming back to the key takeaways, kind of hitting the nail on the head a little bit too much here, or just repeated. Video recording angle matters. Limited influence movement pace, especially if we record from those optimal views. And before I get into a little bit of a summary, I just kind of want to show an initial comparison across the companies. Again, just to kind of show that we're seeing it across all the companies that we've been looking at, and not just 1 or 2 companies driving the data that we're seeing. So this is an initial comparison across companies. This is going to be focusing in on the left shoulder elevation angle from the views on the left side of the person. So kind of narrowing our scope a little bit. And for the palletizing task on the left, again, across all of the companies, we're seeing that the left camera angle is generally producing the lowest root mean square difference across all the companies. Going to above shoulder work, so the graph on the right, the left side producing the lowest root mean square differences or differences from the companies compared to the Thea Markerless. And again, that's generally across most of the computer vision tools. So we haven't done any statistical tests between computer vision companies as we are still processing that part of the data, but that is part of our analysis going forward. So again, key takeaway here, similar results in interpretation across the 5 different companies that we've been using. So if we add that in to our key takeaways, we see subtle differences, but similar results in interpretation across the companies. But again, we're still analyzing a little bit and haven't run any statistical analysis. So this is the results so far. So what does this all mean for ergonomics now? So using these computer vision tools, went a little bit ahead there, is not as simple as just point and shoot. We point, capture, upload a video, boom, Bob's your uncle. You have a completed risk assessment. You have your answers, go from there. It's not as simple as that. So with everything that we've learned and presented so far, capturing good quality data will allow you to perform some risk assessments. And you also require the appropriate training and guidance to capture that data appropriately and to interpret the data appropriately as well. So the saying that I like to use is kind of good data in, good data out, or bad data in, bad data out. So if we are using everything that we've learned, capturing good quality data, using that as and putting that into these computer vision tools, we can then do some assessments that way. Alongside this, part of our goals with the study is to create a best practice guidance document or infographics to help users best understand how to use these computer vision technologies to capture these good quality data. So once we have everything wrapped up, we're going to be working on these documents as well, and just to get the best practices out there. Now, also in what's happening now is we're seeing a lot of these companies integrating existing single task assessment tools like NIOSH, Strain Index, REBA, RULA, Liberty Mutual Equations. Starting to see a little bit of hand activity level as well, depending on the company. And while these assessment tools are mainly posture based and do require some inputs such as like hand height, vertical displacement, frequency, duration, etc., I believe that these technologies are working to help companies, ergonomists, and practitioners perform these assessments in a more automated way, and in hopes of freeing up some more time to focus on creating those solutions. So again, it's not as simple as point and shoot. And again, you get the data you want. You need to have appropriate training, guidance, capture good quality data, and be able to evaluate and interpret the data and risk assessments that are coming out of it, and not just kind of take it as gospel. That's what I'm trying to say. So in principle, I think this is a great step for ergonomics now. But again, like not simple as point and shoot, and requires some good data and good guidance to capture that good quality data. Now, before I talk about how this technology can be used in the future, I kind of want to put this in context with some previous work surrounding a 2.5-year long Ontario University's back pain study. Now, this study examined physical and psychosocial risk factors associated with low back pain in workers from General Motors Canada. And in the study, they captured videos of workers on various jobs on the production lines. And they set up these cameras to view the major plane of motion, which was flexion extension, and they set them up to view from the side. So again, similar to all the results that I presented here, this is just going and backing up research that was done previously. So our data is suggesting the exact same best practices as what was used in the past. Now, all these videos were digitized, and an operator or an assessor used a computer program to manually enter the postural information to match stick figures and postures with the video that was captured. And they did this frame by frame. And this is very, very time consuming. Now, from this work, many seminal studies use this data set to identify several biomechanical factors associated with reporting low back pain. Some are peak and cumulative spine loading, peak spine flexion, flexion velocity, etc. These are very influential works, and they no doubtly took a long time to collect and analyze and process, and especially going through all those videos to capture and posture match frame by frame. But now what I'm bringing this back to is now in the future, what this technology means for us now is that we can have the ability to capture these time series data in the workplace and analyze these data in both time and cost efficient manners. Again, when these data are captured using the best practices approaches that we are continually learning about, it can lead to the development of extremely rich databases of movements outside of just lifting or flexion extension that occur at various jobs that could be used in further epidemiological work to identify and characterize injury risks in the workplace. And one of the areas of immediate interest is trying to quantify cumulative loading exposures for joints throughout a workday or work shift. Now, with the landscape of modern work changing to involve more multitask work or trying to measure cumulative exposures across many different tasks, if there are job rotations, it is becoming increasingly difficult. And using the single task assessment tools to take snapshots of each and try and put them all together is very time consuming. However, we believe that this computer vision technology can be used to capture time series data across multiple different tasks, and then can be used in modeling approaches to estimate cumulative loading exposures that are on specific tissues of the body, estimate some fatigue development over multiple different tasks, and kind of work in some of those more cumulative loading exposures and risk assessments in the field. Now, before I turn it over for any questions, I just want to quickly summarize and remind everyone that these computer vision tools have been built on machine learning algorithms to identify key points on the body. These models are a continual improvement process. As we feed it more data, they're going to learn more about the data, get more accurate. And given the recent and continued advancements of these technologies, I would argue that we are still in the infancy or early childhood phase of these technologies. And as they learn and continue to improve, or they will learn and continue to improve as we continue to use them. So again, this is just it's a newly emerging tool. A lot of information that can be captured very quickly, and I think that can be used for very useful research in the field, and taking that field data and finding or applying it to epidemiological research to get some more risk assessments in the field. Now, with that, I'd like to thank the team for all their work in this, thank all of our collaborators, and I'm opening up to you for any questions.
Great. Thanks, Dennis. Before we actually start the questions, just a reminder to everyone, we are going to be posting the Slido survey post questions. So if they can please take a moment to answer that while we ask the questions to Dennis. So Dennis, the first question was, it's interesting that the root mean square difference was worse than moving slowly. Any hypothesis why?
Yeah, this was a little bit perplexing for us as well when we initially looked at this data. So with I can't remember if I mentioned it, but the fast trials are double the speed of the slow trials. So effectively, the amount of data within each of those trials is doubled for all of the slow tasks. So that means there's double the amount of data points, double the amount of chances to be different compared to Thea. And I think that is what is essentially driving those slightly higher differences for the slow data set compared to the fast. Now, what's interesting is maybe if we time normalize to similar amount of data points within each, that could potentially take away that differences. But we haven't looked at that yet. It's something of future interest.
Okay. Based on what you've seen, any recommendations on technologies that could be used based on their data source for workplace applications?
Just maybe a potential clarifying for that. Each of these companies are being used by many corporations incorporating these computer vision technologies into their ergonomics applications. All of them have slightly different tools that they're building into their, I'm going to call it their Ergo application. So when you're looking to figure out which one is going to be working best for you, I would just contact them, see what technologies they're working with. Is it going to fit into your Ergo program? Some of them are more performance-based. Some of them are more of a systems-based approach and time measurement. And some have incorporated different static ergonomic tools within them and are trying to work on validating. So they're all at different stages. So it just kind of requires a little bit of exploration to figure out what is going to work best for you.
Okay, great. From a practical approach with prevention in mind, rather than research, do you recommend these phone-related tools to create an understanding regarding which vocations, positions, or tasks pose the greatest ergonomic risks?
Yeah, I think that this could be a very valuable way to collect what I'm going to call big data. It's kind of a term that is kind of being thrown out a lot. We have really had limited access to capturing time series data within the field in time and cost efficient manner. So just thinking if we want to do this now without the computer vision approaches, we would have to bring in an IMU suit or inertial measurement units or multiple cameras and set them up and calibrate the system. This is ultimately going to slow down the production processes, and many companies won't allow that. But having this quick tool in there will allow us to capture that time series data, which can then be put together from multiple tasks, multiple workplaces, and then we can potentially in the future start to look at some relationships between injuries that are being presented in those fields with the motion that's happening. So it's a long-term outlook for how these tools can be used to look at injuries in different workplaces and different tasks and across different sectors as well.
Okay, great. Well, thank you, Dennis. That appears to be the last question. I look forward to seeing what's coming in the near future with respect to all this technology, as you and I discussed earlier. It could be almost ground changing, or it's almost scary what we could be seeing happening. So with that said, Dennis, I'd like to thank you for participating today, and also thank you everyone for being here, and hopefully we'll see each other again next week.